Hello everyone, my name is Anthony Shivkumar, and in today's video I want to go a little basic. I want to talk about Maxwell's equation, and the reason being is eventually I would like to basically construct my own brushless DC motor, designing high-speed designs, and you'll realize that his equations crop up a lot in just the whole breadth of creating a drone right from the grounds up. You realize that they're fundamental concepts that are right there in these equations that keep cropping up no matter what you do. And I thought it would be a good idea to go through Maxwell's equation and to just get a sense of how they work, as these equations explain things that we take for granted, in the sense, electric flux or electric field, or what's a curl or what's a divergence, and how does a capacitor charge, or how is electricity and light exactly the same thing? How are they both part of the electromagnetic spectrum, which has basically enabled half of civilization today in terms of Wi-Fi and internet and all the cool stuff that we have, including our mobile phones, and it's all grounded in these equations. Not to mention, and from a practical electrical electronics standpoint of creating a drone, you realize that these things come or are very prevalent when you want to design your own motor. How do the forces act? How do you make a motor that's efficient, and and how do you design and construct it, and how does the magnetic effects, the electric effects affect the overall efficiency of your motor, and you'll realize that they're all grounded in these principles. How does a capacitor work? How does a capacitor store charge? It's all again grounded in these equations. So enough of talking about the practical implications. More or less everyone knows about that, at least at this stage. What we're going to do over here is look at equation. There are 4 equations that govern the Maxwell's equations, and I'm just going to focus on one of them, and we're going to go distill and basically break apart those equations step by step, understand what every parameter of those equations mean. In a nutshell, I want us to see through the equations so that we have a better understanding, a deeper understanding of how these things work. So the first thing that we want to focus on is that Maxwell's equations can be generally classified into at least the 2 types of fields or electric fields that govern the Maxwell's equation. Is the electrostatic field, and that's basically an electric charge, which could you have these experiments where you rub a ruler on your head, and then it's able to pick up paper, because it's you're creating you're polarizing a charge in one of your in your ruler, and that's basically creating a charge on another object, such as a paper. So those are basically electrostatic charges. We also do this even in protecting ourselves from damaging equipments. We have something called as electrostatic discharge, where you wrap this around yourself, and all the charge that's there in you, that's built into you try to ground them. So it's kind of always there. And that's the first type of effects that this Maxwell's equation basically talks about. The second one is got to do with the magnetic and electric field, which basically means that if you change the magnetic field, you can induce an electric field, and vice versa. And this is grounded in practical applications such as motors, transformers. Like, these principles literally govern modern technology and the industrial revolution. Because we're able to realize that with magnets you can create, an electric field, and with an electric field, you can create a magnetic field, and vice versa. And as I mentioned, motors, transformers, and many things related to power, electronics, are governed in this principle. So that's the idea of Maxwell's equation, at least at a high level. It's talking mostly about Gauss's law, Faraday's law, Ampere's law, and a combination of these laws to create the 4 laws or the 4 equations of Maxwell's. Now, let's go to the first equation. Generally speaking, every equation of Maxwell has 2 forms. One is the integral form, and one is the derivative form. They both are basically two sides of the same coin, and they allow to explain different phenomena related to the same equation. So in today's video, I'm only going to talk about the integral form and of the first equation, basically, of the first equation amongst the four equations. So what does the first equation talk about? It basically says that an integration over a surface area of an electric field multiplied, I won't say multiplied, it's a dot product because these are vectors, of a normal of that surface area is equals to the charge enclosed in that area divided by the permittivity of free space. The way I've explained it is basically gibberish, at least to an average user. If someone explained it to me what this is doing, it's basically what the heck. In a nutshell, we can think about the left-hand side as the flux, which is a word that we basically hear a lot, and especially if you're doing anything electrical, electronics, dealing with motors, transformers, basically power electronics and the machines that govern power electronics. You'll use the word flux, and this is nothing but flux. And the right side is charge enclosed. Again, what does all this mean? So we're going to break it down step by step. Now in the integral form, I've just broken it up as descriptive as I possibly could. The integration is an integration over a closed surface. This is what the circle means, and we're taking a surface integral. And when looking at the contribution of every charge on that surface. So this is what this integration is doing. So it's creating the surface area over a closed surface. E is the electric field vector. And this is a dot product. And a dot product is applied where E is a vector and N is a unit normal vector. And a unit means it's 1. A normal generally means it's perpendicular to a surface. And this is basically flux. And I'll explain a little bit more to it, but I'm just trying to, break the equation to see, what it's really doing. And this is equals to the charge enclosed divided by the electric permittivity of free space. So in a nutshell, what this equation is trying to communicate is if you have a charge over here, which is this enclosed charge over here, this is equal to the amount of charge that is there on the surface area. Or if you want to know if you have all the surface of, if you have the known amount of charges that's there on the surface, you can figure out what is the charge enclosed in it, vice versa. And the electric field that passes through the surface, we call this flux. So basically the charge around that's flowing through the surface, and it could be an imaginary surface, it could be a real surface. In many practical cases, you consider this as an imaginary space that you want to, say, design your product for, and you basically try to figure out how much of flux is passing through it. This could be very relevant when you're doing things like EMI radiation or electromagnetic interference, and you want to basically create minimize this flux that's generated around your product. And if this is the charge of, say, your device, so this is an application that I'm just mentioning over here. But in this particular case, we're trying to say that the amount of charge that's in here is directly proportional or is equal to the charge that's there on your surface. And the electric field depends on the distance. It's not there in this equation, but when you decipher or break down what the electric field actually does, you'll realize that this distance of the charge from the surface does contribute to how much flux this overall surface has. There are a few rules that you want to consider. That electric field lines must originate on a positive charge and terminate on a negative charge. So this is a positive charge, so there's always going to be emitting. And if it's a negative charge, then the field will be going into it. The second thing that we want to focus on is that the net electric field is the vector sum of all the fields present at that point. So if you have a field over here, and if there's a field coming from this direction, from another direction, it is a summation of all those fields at a particular point. So that at any instance, there will only be one vector field, and the cumulative force and direction of all those vector fields will point in a particular direction. And that's what we're basically going to consider. That at every instance, there's only going to be one electric field at that very instance. Electric field cannot cross each other. The net forces is a constant. So basically, you won't have two electric fields crossing each other. It'll always be one, because you're creating the aggregation of, or you're accumulating all the forces, and the resultant force is what we consider. But this is a nutshell of what this equation does. So now what we'll do is break each and every single part of these equations to really get a gist or get an understanding of why this equation is written this way, and what does this really imply. Okay. So the first thing we want to focus on is the electric field, the E basically. What does this E signify? What is an electric field? The way you want to look at it is the electric field is the force acting on a charge, which is a coulomb. So the unit of an electric field is Newton per coulomb. So the amount of force that is acting on a particular charge. Now, if you really want to know what Newton per coulomb really is, this is voltage per meter, or you could basically say that voltage is equals to Newton meter divided by coulomb, and if you take the Newton, it's volt divided by meter, or Newton per coulomb is nothing but volt per meter. So this is basically what this equation implies. And there are a few calculations that we can make from this electric field. So the field equations for simple objects. For example, if you have a point charge, you can say that the electric field is 1 upon 4 pi epsilon 0 into r square, q divided by r square, into a unit vector, which is r. So if you want to find a point charge from an object, so if you have a charge over here and you want to find, and there's a point charge over here, and you want to find the electric field that's between this charge and this charge, you can apply this equation. So it'll basically say 1 upon 4 pi epsilon 0 q divided by r square will give you that electric influence from that charge. And the same equation goes to a sphere. It's the exact same equation. It's just that you have you have just capitalized letter because it's an outside distance from the center. But that's basically what I'm trying to say. Like, it could be a point charge or it could be a conducting sphere. Doesn't matter. The equation is very similar. 1 upon 4 pi epsilon 0 q divided by r square, where q is basically an outside distance r from the center, but it's still a charge. The q is the charge. This is small and this is capital, but it's exactly the same formula. And you can find the electric field that's acting. If you have a sphere on the other side or at a distance, you can calculate the electric influence or the electric field between this point charge and that sphere. So this is what the electric field is. It's a force per coulomb. So it's a Newton per coulomb. Just remember this. It is a confusing concept as to what this electric field actually does, but it's a force. Think of it that you can feel this in some shape or form. Like it's very real in some shape or form. Now let's break apart different parts of this equation. So there's a dot product right over here. And the dot product signifies a lot, especially in vector calculus or vector algebra, vector mathematics. There's a dot product and there's a cross product. And the dot product of any two vector products is always a scalar product. And that's what we're going to focus on next. So A dot B is always going to be a scalar product. So if you have A in the X direction, Y direction, and Z direction, what is a vector? A vector has a magnitude and direction. So if I take A across the X component, B So basically, if you're doing A into B and it's a three-dimensional vector, you'll have the X components multiplied by each other, plus the Y components multiplied by each other, plus the Z components multiplied by each other, and you'll have a scalar quantity. Basically, you'll have one number. It can also be written as the magnitude of A into the magnitude of B multiplied by the magnitude of B multiplied by cos theta. Or a way of looking at it is basically saying that if A is an angle between A and B, there's a two vectors and there's an angle, you're projecting A onto B and then multiplying that into B. That's really what is happening. So you're projecting one vector onto the other vector by cos theta, and where it falls, you're multiplying that with B. And you can do the same thing and project B onto A. And this has some implications when we look at the Gauss theorem or the Gaussian formula as a whole. But this is what this dot product is actually doing. It's taking a vector from here, it's projecting this vector onto B, and then creating the resultant by multiplying it by cos theta. And to get the magnitude of A, you basically take the square root of ax square plus ay square plus az square, and that will give you the magnitude of A. Similarly, for B, you take the square root of bx square plus by square plus bz square, and then you'll get the magnitude of B. So these are the magnitudes of A into B into the cos theta. The third part of this equation, as you'll see over here, there is a normal over here. So there's an n over here. It's a vector. It's called a unit vector normal. And let's decipher this a little bit more. So the unit normal vector, which is the n hat, there are two words that basically explains what this does. One, it says it's a unit vector. So that means it's one. It doesn't have a unit. It's one. You just multiply. It's like multiplying anything by one. It's just one. It's a unit thing. And normal means it has to be perpendicular to a surface. Now, if it's a plane, it'll always be perpendicular. And if it's a surface over here, it's just going to be in the direction that's perpendicular. So if it's in the North Pole, it's just going to be facing upwards. If it's the South Pole, it's going to be facing downwards. So this is what a unit vector normal is. And in Gauss's equation over here, we're trying to basically take the electric field and dot product it by the unit normal. And in a nutshell, we're taking that electric field that is coming out of, which is emerging, whether it's positive or negative, and we are basically projecting it onto the unit normal to find the resultant electric field at that particular instance on that surface. That's what this dot product is actually doing. So let me, I'm just going to leave this over here because this is an important sheet. And we focus on this as well because I'm constantly going to refer to these equations as we try to break it down one step at a time. All right. So this is what the E dot N is going to do. So this E dot N, which is over here, which is part of this equation, is we're taking the vector of E, and it could be in the X, Y, Z direction if it's three-dimensional. We're multiplying it with the unit vector. The magnitude of the unit vector is always going to be 1, cos theta, which is nothing but electric field multiplied by cos theta. And if the force is perpendicular to it, that means cos theta is equal to cos 90, then it's going to be 0. So that means it is going to be, if the force is acting perpendicular to the unit vector, then the resultant force is 0. But if the force is parallel to the unit vector, then it's going to be cos 0 is going to be 1, which is basically the full electric field. So you're basically trying to calculate the resultant magnitude of the electric field. And if it's normal, it's going to be the full electric field's magnitude. And if it's not normal, if it's not parallel to the normal, then it's going to be a little weakened by the factor of cos theta, basically the angle at which it makes to the normal. So that's what this E dot N basically signifies, is that we're always trying to figure out whether the field is perpendicular to basically we're calculating it to the normal of the surface of the imaginary surface that we're trying to calculate. The last part is, or the couple of parts that we're going to break down now, is the integral part. What does this integral part mean? So you'll have it's a surface area with dA, the surface integral. So let's get and make a simple example. Say I have a small little area over here, which has got a length and a width, and I have a mass in each one of these small little blocks. Now, if I ask you what is the total mass of this whole area, and each one has, say, a mass of m1, and each one is m1, 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 or you can basically say m. So then you can say that the total mass of this whole product is going to be the L into the width multiplied by m, because that's basically the mass of this object, if each one of these small little squares has a mass of m. But what if they're not equal? What if one is m1, the second is m2, m3, m4, m5, m6, and each square is little different? Then one thing that we could do is basically say a sigma 1 into the area of 1 plus sigma 2 into the area of 2, which is basically the mass of each one of these small little blocks. And then you do the summation of all of them, which is basically the summation of all of these. And in mathematics, to interpret this summation, which is something that we, instead of constantly adding all of these things, is a formula that we incorporate in mathematics, and that's the integration. And the integration is basically breaking this into such small pieces that you basically are able to calculate this whole area with this gradient of mass. The mass is not constant, and it could be it's basically calculating the distribution of these masses over an area, or the distribution of forces over an area. And this is what the symbol does, the integration symbol does. So you integrate over 0 and a, you'll know the formula for the sigma, how the mass is distributed, and then you're basically able to calculate the total mass of this particular object. In a similar way, for the vector field that we have over here, a dot n over the surface area. Now, if everything is just normal, parallel to the normal of this field, the flux is going to be a into the surface area, because everything is normal to it. There's going to be the full magnitude. If there's an angle to it, then you'll have a dot n into the surface area. All right. And what if the force itself is not constant? The force itself is not constant, and they're all attacking at different angles. This is where this kind of a general formula may not necessarily apply, because now it's changing. And one thing you can do is basically say the force acting on A, that is perpendicular to one of those unit vectors, are multiplied by the area, and you keep summing all those parts. And in simple English, what we're trying to do is basically taking an integration of the area vector, which is basically the electric field, passing through this normal of the surface area, or the unit vector. And this is how we represent this charged surface, or this closed surface. So this is the circle over here means closed, S means surface area. So we're taking the integration of a closed surface with the forces acting on A, the dot product of a unit vector and its area. So that's how we're representing all the forces that's acting across this surface, which would have different magnitudes in different directions, and we're trying to calculate it with respect to its to the unit vector. And that's how you represent this. And I also mentioned over here, as mentioned over here, that this dot product A dot B is basically the magnitude of A into B into the cos phi. So this A dot B over here, A dot N, is nothing but magnitude of A into magnitude of N, which is B1, into the cos theta. So this angle will always be the angle bit of the unit normal with the angle of the force acting on it by cos theta. And in this case, cos theta is going to be, it's a parallel, so it's 0 degrees, so cos 0 is 0. As I mentioned in earlier over here. So cos 0 will be, cos 0 is going to be 1, and cos 90 is going to be 0. So cos 0 is going to be 1. So because it's 1, it's always going to be, it's going to take the full magnitude of the force acting on it. And if it's angled, then it'll be A dot N, and A dot N will be A magnitude of A multiplied by the magnitude of the unit vector multiplied by cos theta. Now let's go and move on to the electric field through a closed surface. So just as we broke down this as A dot N, we're going to decipher this as E, the electric field, dot the normal vector, to get a full understanding of what this equation is doing. And over here I have it as the electric flux, which is equivalent to the number of field lines penetrating the surface. And that's what an electric flux is. So I basically created a formula for this, basically saying that the amount of field lines that penetrate the surface is nothing but an electric flux. And you don't see these field lines. It exists, but it's always continuous. You don't see it, you don't feel it. I mean, you can definitely feel the effects of it. That's how motors and transformers work, and EMI would work. Electromagnetic interference, basically noises, but that's what a flux is. It's the number of field line penetrating a surface. That's how you should be looking at it, and that's how it should be perceived. And that's the left side of this equation. The number of field lines penetrating through a surface, you can calculate that by the dot product of E, the unit vector, and the area. Now let's focus on the right side, which is this cube enclosed over here. So the enclosed charge could be something that I mentioned earlier in this lecture, where you have a circle over here and you have a dot and a small little charge over here, and this could be a point charge, and you could have multiple point charges. So here you have one point charge, or you could have multiple point charge, or you could have a line charge, and basically in a one-dimensional object, you basically could have this as lambda L. If it's a uniform charge, then you can basically call this lambda L. If it's two-dimensional and it's uniform, you can call it sigma into the area. And if it's three-dimensional, you'll have rho into the volume. But if it's not uniform and it's distributed, but it's non-uniform, then you just have an integration over the lambda into dl, integration of the area, which is sigma into dA, which is a small little area. You basically take small, that's how integration works, into dA, and this integration of the volume of rho dV. So a point charge is the lambda into L. All right, so the length multiplied by the value of lambda. In this particular case, that would be the coulomb itself, or the charge itself. And the last part of the equation, so that's the amount of charge of the enclosed within the enclosed area. And the last part is the permittivity of free space. The permittivity of free space is which is epsilon, which is called 8.85 into 10 raised to 12 coulombs per volt meter. This is a response to an electric field. So if you have an electric field flowing through an object, and if there's no dielectric present, dielectric is nothing but it's an insulator basically. It does not conduct, or it limits the current flow of current. At a certain voltage, it will eventually break down. They'll have a breakdown voltage, but for the most practical purposes, they don't allow electrons to flow freely. So they're not conducting in nature. So if you don't have any dielectric, then the electric field just flows through. But if you have a dielectric, the field can still flow through, but at the same time, while it's doing this, it's going to limit the field from flowing through, first and foremost. But it's also the dielectric will also start to present, it also has few electrons that will align itself. And it'll basically create a charge. And because it is coming in, this side is going to be negative. And because this part of the field is coming out from the side, we're going to cause this positive. So if there's no charge at all, then you could have that these electrons or these charges are now displaced within the dielectric. And then eventually it will start to conduct from positive to negative. So it'll basically flow from one direction to the other. And this is how a capacitor works basically. So a capacitance is basically the rho area, the area between the capacitance plates divided by the distance. So the further the distance is going to be less the capacitance, smaller the distance. It's inversely proportional to the distance. And E would be the dielectric constant or the epsilon over here, the permittivity of free space. And if you take this Q enclosed, the charge enclosed, divided by the permittivity of free space, which is a dielectric constant, if you think of it that way, that should give you the total charge that this particular that this particular enclosure would have. So in a nutshell, this is the first law of Maxwell's equation, where the electric flux is equals to the total number of charge enclosed, and you'll have this equation come up all the time, especially when you're designing motors. At least in this particular case, for my practical purpose, while I was studying and designing some part of the motors, brushless DC motor, some shape or form of this equation kept cropping up, and I thought it would be a good idea to do this a deep dive into Maxwell's equation. And that's what we have over here. I hope this made sense. And if you like this video, do subscribe. And in the next part, we'll go into the derivative form, and we'll also might talk about the second Maxwell's equation, which is going to be related to the magnetic effects of the electric field. In this particular case, in the static charge, to keep in mind is that the electric can be positive and negative. They don't always have to be together. An electric charge can either be positive or it can be a negative charge. But when it comes to magnets, there's always going to be a positive and a negative. And that's what we'll be dealing with next, where they cannot exist individually. You'll always have a north pole, you'll always have a south pole. If you split the magnet, there'll again be a north pole and a south pole. You cannot distinguish between, you cannot have a magnet which only has a north pole or a south pole. You'll always have both. Whereas in this particular case, you have a charge that can either be positive or negative. They don't always have to be together. So you can always, that's the difference between the electrostatic fields over here. And then in the second equation, we'll be talking about the magnetic effects of these equations. All right. Thank you.